The quantum vacuum, a sea of virtual particles. Title: The quantum vacuum, a sea of virtual particles. Introduction, 150 words. The quantum vacuum, also known as the zero-point field, is a fascinating concept that explores the mysterious nature of space itself. Often misunderstood, the quantum vacuum is not a classical vacuum devoid of all matter but is instead a bubbling sea teeming with virtual particles that briefly flicker in and out of existence. According to this theory, empty space is not empty at all but is rather filled with a background of constantly fluctuating energy. These fluctuations give rise to virtual particles, which spontaneously appear and annihilate each other in an incredibly short amount of time. Virtual particles, unlike the particles we are familiar with, do not obey the restrictions imposed by conservation laws. They can violate the principle of energy conservation due to Heisenberg's uncertainty principle, which allows for temporary deviations in energy levels as long as they are short-lived. These virtual particles can vary in type, including photons, electron-positron pairs, and even the more exotic particles predicted by the Standard Model. However, it is important to note that these virtual particles do not have the same properties or effects as their real counterparts. Experimental evidence, 350 words. Although virtual particles cannot be directly observed, their effects can be experimentally detected. The fluctuating quantum vacuum generates a pressure imbalance between the plates, causing them to attract each other. This phenomenon has been successfully measured, providing indirect evidence for the existence of virtual particles. Another experimental confirmation of the quantum vacuum's existence comes from particle accelerators. These powerful machines accelerate particles to extremely high speeds and energies, allowing physicists to recreate conditions similar to those in the early universe. During these experiments, the presence of virtual particles is inferred from their influence on real particles, such as alterations in their trajectories. Implications and applications, 500 words. The quantum vacuum and virtual particles have far-reaching implications for our understanding of fundamental physics and the universe. They play a vital role in several phenomena, ranging from the stability of atoms and the behavior of subatomic particles to the expansion of the universe. One significant application of the quantum vacuum is in the field of quantum electrodynamics. It is a theory that combines quantum mechanics with electromagnetism and has been successfully used to describe and predict various phenomena with remarkable precision. Virtual particles significantly contribute to calculations, enabling the prediction of properties such as the anomalous magnetic moment of particles and the fine structure of atomic spectra. Moreover, the quantum vacuum may shed light on the nature of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe. Several theories suggest that dark energy arises from the energy density of the quantum vacuum. If this is true, it would mean that the quantum vacuum's energy accounts for a significant fraction of the total energy content of the universe. Furthermore, the study of the quantum vacuum has implications for our search for a unified theory of physics, as it challenges our current understanding of matter and its interactions. The behavior of virtual particles in the quantum vacuum might hint at the existence of yet-to-be-discovered fundamental particles or even new dimensions beyond our current understanding. The quantum vacuum, also known as the zero-point field, is a captivating concept that revolutionizes our understanding of the cosmos. It challenges the notion of empty space and reveals a bubbling sea of virtual particles. These virtual particles, constantly flickering in and out of existence, are the product of fluctuations in the quantum vacuum. To truly comprehend the quantum vacuum, we must turn to quantum field theory. This theory explains the behavior of particles and fields at the quantum level. It posits that space is not devoid of matter but is filled with fluctuating energy. These fluctuations give rise to virtual particles, which momentarily appear and annihilate each other. Virtual particles are distinct from the particles we typically encounter. They do not comply with conservation laws and can violate energy conservation due to Heisenberg's uncertainty principle. This principle allows for temporary deviations in energy levels as long as they are short-lived. Virtual particles can come in various types, including photons, electron-positron pairs, and other exotic particles predicted by the Standard Model. However, they do not possess the same properties or effects as their real counterparts. Although virtual particles themselves cannot be directly observed, their effects can be detected through experimentation. One notable demonstration is the Casimir effect, first predicted by Hendrik Casimir in 1948. This effect occurs between two uncharged parallel conducting plates brought close together. The fluctuating quantum vacuum generates a pressure imbalance, causing the plates to attract each other. This phenomenon has been successfully measured, providing indirect evidence for virtual particles. Particle accelerators also offer evidence of the quantum vacuum's existence. These machines accelerate particles to high speeds and energies, recreating conditions similar to the early universe. The presence of virtual particles is inferred from their influence on real particles, such as alterations in trajectories. The implications of the quantum vacuum and virtual particles span various fields of physics and our understanding of the universe. They contribute significantly to quantum electrodynamics, which combines quantum mechanics with electromagnetism. It accurately predicts properties such as the anomalous magnetic moment of particles and the fine structure of atomic spectra, thanks to virtual particles' influence in calculations. Furthermore, the quantum vacuum may hold the key to comprehending dark energy. Dark energy propels the accelerated expansion of the universe, and some theories suggest that it arises from the energy density of the quantum vacuum. If this is true, it implies that the quantum vacuum's energy makes up a substantial portion of the universe's total energy content. The study of the quantum vacuum challenges our current understanding of matter and its interactions, impacting the search for a unified theory of physics. The behavior of virtual particles within the quantum vacuum may hint at undiscovered fundamental particles or dimensions beyond our present comprehension. The quantum vacuum, also known as the zero-point field, is a captivating concept that revolutionizes our understanding of the cosmos. It challenges the notion of empty space and reveals a bubbling sea of virtual particles. These virtual particles, constantly flickering in and out of existence, are the product of fluctuations in the quantum vacuum.